In the previous lecture, we had obtained the energy functional for a static meniscus. The energy functional, which is nothing but the free energy of a static meniscus, depends on the function h of x, where h of x is the height of the meniscus. And this is basically written in an integral form, where we basically integrate over the entire extent of the static meniscus going from 0 to b. And the integrand is shown by another function, which is capital F, which is in itself a function of h and its derivative hx. And we also have the changes to the surface energy of the solid when the meniscus rises to a height of h0. We had already obtained the shape of the meniscus by using a force balance approach. What we want to do in this lecture is to derive the governing equation for the shape of the meniscus using an energy minimization. Now, I'd also shown that if you have an energy functional or any functional which depends on another function, let's say in this case like E is a function of h of x. Now you can clearly see that the integrand involves a new function capital F, which is in turn a function of h and hx. So capital F is like a Lagrangian in Lagrangian mechanics. Then this capital F has to satisfy the Euler-Lagrange equation. So that's also shown in this equation here. The Euler-Lagrange equation, I have written it in the form that we had derived in the last lecture. Now here y has to be replaced with h and y prime has to be replaced with h prime or hx. So what we will do in this lecture is to take this energy functional and in the way that we have written down, and we'll apply the Euler-Lagrange equation. Now there's also one more step that we have to do, which is to ask what happens to the last term that is there, which represents the changes to the surface energy at the solid. Now what we want to also do is to derive the relationship between the meniscus slope at the wall and the angle, the contact angle theta e. So in other words, we want to also comment the approach that we're going to employ now, which is energy minimization, will also lead us to the boundary conditions at the contact line, that is at x equal to 0. So let us proceed by first taking a look at the energy functional that we have here. F is written as in terms of h and hx. Now since we have h as a function of hx, we will modify the Euler-Lagrange equation. Instead of basically writing in terms of y, we will write it in terms of h, and in this case we'll write it in terms of h prime, where h prime is nothing but hx, that is dh by dx. Now let us write the functional again, not in terms of x but h prime, just for the sake of it. So if this quantity E is a function of h of x, which recall is given as gamma SL minus gamma SG. I'm writing the last term first. This is multiplied by h at x equal to 0, which we had called as h0, plus an integral going from 0 to b of this quantity f, which is a function of x, h and h prime dx, where this quantity f is nothing but gamma 1 plus h prime square whole power half plus half rho g h square. Previously I used to use the subscript x to denote the derivative of h with respect to x, but since we had basically done the analysis when we derived the Euler-Lagrange equation, we had used the notation prime to denote the derivative. I am recasting our results in our equations in the format that we derived in the previous lecture. So now we have the energy functional. Now we can also say that if we have an arbitrary meniscus as shown here, and let me erase a few things here. Now I want to perturb this. I want to look at a small deviation from this. Now h of x, what is it here? H of x is the extremal that we are interested in. So this quantity here, h of x, this is already the extremal of E. Extremal of E means it is the shape which will give us the minimum energy E. That's what we are looking for. But it is possible that this function, the shape that we have here, h of x, may not be the, let's consider an arbitrary deviation from it. So at any point, I have a small deviation that I have introduced, and this deviation that I have introduced here is, let's call it as delta h, right? So delta h clearly is a function of x. So delta h is small, okay? So magnitude of delta h is much smaller than magnitude of h at any location. And therefore, what I now have is, if E satisfies this equation, then the general expression for this functional, which is h plus delta h and h prime plus delta h, will simply be gamma SL minus gamma SG of h plus delta h at x equal to 0 plus this Lagrangian f, which is at x, h plus delta h, h prime plus delta h prime dx. So this is what we had done also in the derivation of the Euler-Lagrange equation. We had called this the quantity h bar. Okay. So now we have the expression for the functional, where we basically are not at the extremal shape, but we are at a different shape. Okay, we are on the green curve now. And so the idea is that we want to basically shrink the size of this delta h to 0. And when we do this, then my interface shape will coincide with the extremal shape. Okay. So now I can just say variation in E. I'm just taking a slightly different approach to what we had done in the previous lecture. But essentially the idea is the same. Variation in E is given by, let's call it as delta E. How do we get this delta E? What we do is we take a Taylor series expansion of E about h of x. Okay. We can take a Taylor series expansion of E about h of x and h prime of x. Okay. So let me write that down. Since the variation in h of x is small, we can take a Taylor series expansion involving two functions, or you can even say you can treat them like variables. H of x and h prime of x. Okay, so what will this give me? It will tell me that E at h plus delta h prime plus delta h essentially is going to be gamma SL minus gamma SG of h at x equal to 0 plus delta h at x equal to 0. This is the first term. Now the next term essentially would be, I have to take a Taylor series expansion of this quantity f about h of x. So what we have now is, we have 0 to b. The first one is just the original function f or x h h prime plus del f by del h into delta h plus del f by del h prime into delta h prime plus so on. So this is my Taylor series expansion, and so this is, now I have got E. So let's basically label them. So my equation, this equation I'll call it as 3. Equation of E at h plus delta x and h prime plus delta x is given by equation 4, and we have now 5. Okay, so now I can do subtracting. We have the expression without any variation. We have the expression given by equation 3. Subtracting 3 from 5, what do I have now? I have E at h plus delta h, h prime plus delta h, minus E, h and comma h prime. This quantity essentially will be equal to delta SL minus delta SG. The only thing that will survive now is delta H at x equal to 0. The first term will cancel out on the right hand side in equation 5. And then we have this term here is same as what we had earlier. This term that I am basically putting at a star is same as this term here. So basically again these two get cancelled out, and what gets left out is only the term, those two terms in the integral. 0 to b, I have del f by del h of delta h plus del f by delta h prime of delta h prime dx. This is what I have, and this quantity on the left hand side we label it as delta E. So we want to minimize the energy. So in other words, when delta H goes to 0, meaning the variations of the interface shape about the extremal shape h of x goes to 0, then this delta E goes to 0. So now what I have now is delta E is simply going to be gamma SL minus gamma SG of delta H at x equal to 0 plus, now if you look at the second term here, I can do integration by parts for this. Integration by parts. Let's write down the first term here. The first quantity will be del f by del h prime times the integral of del h prime, that is del h. Okay, this has to be evaluated from 0 to b. Then I have the second one would be 0 to b, the derivative of the first function, that is d by dx of del f by del h prime times the integral of second function, which is delta h prime. The integral is delta h dx. Okay, that's the integration by parts. integration by parts. Which term these two correspond to? These two terms that we have here, they correspond to the second term that we have here. Okay. Now finally we still have the other term, which is plus 0 to b del f by del h of delta h times dx. So putting everything together, we have delta E is gamma SL minus gamma SG of delta x equal to 0. Then let's write down this term here first. Del f by del h delta h evaluated at the two extreme limits 0 and b. And finally this quantity can be written in this integral form, that is del f by del h minus d by dx of del f by del h prime dx. Okay. So now we have this expression for the variation of the energy when I basically look at variations of the interface shape. Okay. This will call this equation as equation 6. Okay. Now, the first two terms of the right hand side that you see here, that let me just highlight them for your benefit. The first two terms, this term and this term, the first two terms here are determined by the boundary conditions at x equal to 0 and x equal to b. Okay. So we will return to this later, but let us now look at the last term here. Okay. So this quantity here in the curly braces that you see here, this is nothing but the Euler-Lagrange equation for f of x, h and h prime. Okay. So let's evaluate this. Okay. So what is this quantity f of h, h and x prime? Recall that this is nothing but gamma times 1 plus h prime square whole power half plus half rho g h square. This is my f. Therefore, if I have to evaluate this, so del f by del h will simply be rho g h, and del f by del h prime will simply be gamma times half 1 plus h prime whole power half times 2h double prime, and this quantity is nothing but 2h prime. Okay, we don't have another derivative again because this is derivative of f with respect to h prime. So h prime is the variable. So if I take a derivative of x square about x with x, I will get 2x. So in the same way, derivative of h prime square about with h prime will simply give me 2h prime. So I simply have I have a minus here. I made a small mistake here. This is minus half. So now we simply have the 2 cancels out. I have gamma h prime by 1 plus h prime square whole power half. So therefore I simply now have d by dx of del f by del h prime simply gives me, I will leave it to do the calculation. It is gamma times d by dx of this quantity h prime by 1 plus h prime square whole power half, and this after some algebra will come out to be h double prime by 1 plus h prime square whole power 3 by 2. Okay. We should remember that h prime is nothing but hx, that is dh by dx. Okay. Now this is the curvature term that we had derived earlier. So now let's put the Euler-Lagrange equation. Euler-Lagrange equation. What does it say? It says that del f by del h minus d by dx of del f by del h prime is 0. This is what we said, okay? And this simply reduces to del f by del h. What is del f by del h? That is rho g h minus d by dx of del f by del h prime. That's just right there in front of us. We have gamma h double prime by 1 plus h prime square whole power 3 by 2. Or in other words, we have, and this quantity is 0, we simply have h double prime by 1 plus h prime square whole power 3 by 2 is equal to rho g by gamma times h. This is same as the, let's give this a label, we call this as equation 7. Equation 7 is identical to the governing equation for the shape of a static meniscus. Static meniscus obtained from force balance. Okay, but what is interesting about this is I never had to know what is the curvature at all. I did not have to know what is the expression for the curvature, what is the normal vector. So if you notice my sketch that I had made earlier, there I've deliberately not shown normal vector because I don't need to know what is the normal vector, what's the relationship between the normal vector and the height, and also what is the expression for the curvature. So we've simply followed the energy minimization approach. We said this is my total energy. It's a combination of surface energy and gravitational potential energy. And then we know that if we have a Lagrangian or a function f which depends on h and x prime, and if I want to find out the shape h of x which extremizes this functional e, then I know that I have to satisfy the Euler-Lagrange equations. The Euler-Lagrange equations for capital F, remember? So I know the expression for capital F, so we just directly substitute it and we get equation 7. Now I could have done this by just saying that, look, this is my Lagrangian, and I substitute it and I get the Euler-Lagrange equation. Now, but I want to do a little bit more. I also want to comment on the other two terms that we had left out. Okay. So what about the two terms that I'm just highlighting now? This term here and this term. What about these two terms? I said these have to be evaluated based on the boundary conditions, right? So let's take a look at them closely now. The first two terms on the right hand side of equation 6 will be determined by the boundary conditions at x equal to 0 and x equals b. Okay, so let's focus on these boundary conditions. What exactly are these boundary conditions? Okay, so the boundary terms in equation 6, what exactly are they? So there are two terms here, that is gamma SL minus gamma SG times delta H evaluated at x equal to 0, and we have del F by del H prime of delta H evaluated at 0 and b. This is my the first two terms of equation 6, right hand side of equation 6. Okay. Now let's these are the boundary terms here. Now let's basically take a look at the interface here. The interface, if I'm at any arbitrary location, and if the angle is theta, and if I focus on this triangle, where if this is delta S and this is delta X, this is minus delta H, what I know now is dH by dx, this is H prime, is minus cot of theta, right? And I also know that sine theta can be written as 1 by cosecant theta, that is 1 by square root of 1 plus cot square theta, this is 1 by square root of 1 plus h prime square, and therefore I have cos theta will simply be, so cot theta is cos theta by sine theta, therefore cos theta is nothing but minus h prime times sine theta, and I know the expression for sine theta now, h prime times the expression for sine theta is 1 plus h prime square, and therefore I have cos theta will simply be minus h prime by 1 plus h prime square root of 1 plus h prime square. That's the expression for cos theta, right? So let's basically look at this here. So I can write down this expression as gamma SL minus gamma SG times delta H evaluated at x equal to 0. And what do I now have here? Del F by del H prime. We have already calculated del F by del H prime. What is del F by del H prime? It is gamma H prime by 1 plus H prime square. I'm referring to this term here, gamma H prime by 1 plus H prime square. So this quantity here is plus gamma H prime by 1 plus H prime square whole power half times delta H evaluated at 0 to H, right? And this simply becomes gamma SL minus gamma SG at delta H at x equal to 0 plus this quantity evaluated at x equal to b. So this quantity evaluated x equal to b. What is the quantity x equal to b? So I have gamma h prime by 1 plus h prime square root of this delta h at x equal to b minus gamma h prime by 1 plus h prime square evaluated at x equal to 0. But notice that as x goes to infinity, okay, where b is very large here, by the way, okay, as x goes to b, okay, and this is approximately same as x going to infinity, where b is so large that the interface essentially has become flat, then h of x goes to 0 and h prime of x also goes to 0. So in other words, this quantity gamma h prime by 1 plus h prime square times delta h at x equal to b basically goes to 0, right? And so now I simply have this expression essentially becomes gamma SL minus gamma SG delta H evaluated at x equal to 0 minus gamma H prime by 1 plus H prime square of delta H now evaluated at x equal to 0. All are evaluated at x equal to 0, right? Now I can basically make one more simplification. For example, instead of writing this as the whole thing evaluated at x equal to 0, I can say this quantity, the first quantity is evaluated at x equal to 0 and the second quantity is also evaluated at x equal to 0. Okay. Now these are my boundary terms. These are just the right hand side, the first two terms on the right hand side. Now I can group them as follows, which is gamma SL minus gamma SG. That's what I have. Now, if you notice here, this quantity on the right, next term that we have, that is minus H prime by square root of 1 plus H prime square, is nothing but plus cosine theta, right? So this is nothing but plus gamma cosine theta evaluated at x equal to 0. This whole thing multiplying delta H at x equal to 0. Okay. So we'll further write it as gamma SL, gamma S minus gamma SG plus gamma cos theta E. This is the theta E is the angle that the interface makes with the wall. That's the contact angle. This times delta H at x equal to 0. Now, you see that it's a product of two terms here. The term in the curly braces that you see, that involves all the three surface tensions or surface energies. Gamma SL, that's a solid liquid surface energy. Gamma SG, it's a solid gas surface energy. And gamma is the liquid gas surface energy or the surface tension. This quantity appears in the first, this is the first term. This is multiplied by, let me emphasize this by explicitly saying that this is multiplied by delta H at x equal to 0. Now if I want the functional to go to 0, so recall that I want this functional in equation 6 to basically the variation to go to 0. I want the functional to be at a minimum. In other words, delta E, if delta E has to go to 0, then we require for delta E to go to 0, we require the above boundary terms. Let's label this above boundary terms as 7, expression 7. We require terms in the expression 7 to vanish. Okay. Remember, there are two terms in the variation of energy. The first two terms that you see on the right hand side, these are the boundary terms. Then the other term, the integral term, is anyway has been set to 0 because we have enforced that the quantity in the integrand is 0 because it is the Euler-lagrange equation. Okay. So the only thing that is left out is the first two terms on the right hand side. After doing some algebra, we have found that the first two terms can be grouped in this nice elegant fashion. These are evaluated all at x equal to 0. Okay. Now for these terms to happen, for these terms to vanish, we either have delta H at x equal to 0 to be 0 or gamma SL minus gamma SG plus gamma cos theta E is 0. So it's a product of two terms. Either this term will vanish, that is the variation of the height at x equal to 0 will vanish, or there is a relationship between the various surface tensions or surface energies involving the contact angle as well. Either this is satisfied or that is satisfied. Okay. Incidentally, this quantity here has a name. So if you look at the second quantity here, this is called the Young's law. Okay. So Young's law says that the cos of theta e, the angle at the wall, is related to the difference in the surface energies, that is gamma Sg minus gamma Sl by gamma. Okay. So we now have two possibilities for the boundary condition. Boundary condition at the contact line. Okay. What are the two conditions? Either Young's law is valid, and if this is valid, then I can straight away apply the condition that cos of theta e is gamma Sg minus gamma Sl by gamma. Note that this cos of theta e tells us I can use this to impose a condition on the height of the interface, on the slope of the interface as it approaches the wall. So in other words, this becomes a slope condition. Okay. So either this is condition or the contact line is pinned, that is delta H at x equal to 0 is 0. So either the contact line is pinned, which means that it cannot move, the contact line position is fixed in space, and therefore it can choose an arbitrary angle, we have no control on the angle, or the angle is fixed and we have no control on the exact position of the contact angle. So if you remember what we had done in the earlier lecture where we did a force balance, we imposed a contact angle condition at the wall. That was the boundary condition that we had employed. If you had imposed a contact angle boundary condition, we are letting the interface rise to whatever height it can rise, that is h naught. Okay. Or we could have done the other way. We could have said, here is the height of the interface. The interface has to meet the wall at this height, and I will say, give me the shape. So now essentially it means that I cannot satisfy the angle, contact angle condition at the wall. The contact angle condition is actually not prescribed in the problem, but is actually determined as part of the solution. Okay. This fundamental difference is very important. It is often not stressed. The subtlety is not stressed. So it's important to note that when we have static problems, either you can choose the Young's law, that is, you can specify a contact angle, or you can specify the contact line position. You cannot choose both simultaneously. Both are not guaranteed simultaneously, at least as far as the theory is concerned. Okay. So with this, let me quickly summarize the key findings of our analysis. We started the analysis by looking at the energy minimization of an interface. So we first, in 2 lectures ago, we basically derived the energy functional. We called it the functional because this energy itself depends on another function, h of x. And we also found that the quantity in the integral, we called it capital F, or you can think of it like a Lagrangian. It's similar to the Lagrangian. This quantity F has to satisfy the Euler-lagrange equations. Then we considered an arbitrary variation of the interface shape, the arbitrary variation to the interface shape, So if h of x is the extremal, we looked at variations to this h of x as delta h or delta h prime. Now we basically did a Taylor series expansion about the extremal shape, meaning we are very close to the extremal shape, and then we found out what is the change in the energy, and we want the change in the energy to go to 0. So the change in the energy is shown in equation 6 here. So this has two terms from the boundary condition. The first two terms on the right hand side are from the boundary terms, and the last term is goes to 0 because the Euler-Lagrange equation is valid for capital F. Now when we employed the Euler-Lagrange equation, we got this equation 7, which essentially tells me that the curvature, so gamma times curvature, that's h double prime by 1 plus h prime square whole power 3 by 2 is the curvature. This is nothing but rho gh, that's the potential energy. So this is the balance of surface energy and potential energy, okay, in another way. So you can think of a balance between hydrostatic pressure and the capillary pressure, okay. This equation 7 was exactly the same as what we had obtained when we use the force balance approach. The one of the elegant things about the energy minimization approach that we have repeated again is that it also tells me something about the boundary condition. Now in the force balance approach, the boundary condition has to be specified by you. So we had when we done that, we just said the angle at the wall is theta e. But now we can actually evaluate that more closely, and we found that, well, it's not always that I can pick the angle. Either I can pick the angle condition or I can pick the position condition. So either the contact line position is specified or the angle is specified at x equal to 0. I can't simultaneously specify both. That will be an overdetermined system if you specify both of them simultaneously, because there is no guarantee that I will satisfy both of them simultaneously. Okay. So with this, we conclude the discussion on the shape of a static meniscus. Now what we want to do next is to look at problems in wetting. It's in a way it's interesting that we have ended this lecture on the Young's law. What we want to do now next is to dive a little bit deeper into the ideas of wetting. So we'll be looking at quantities such as the spreading parameter, what is the contact angle at the wall, and then eventually we look at contact angles on complex surfaces, and then much later in the course we'll also be looking at the contact angle when there is motion as well. So that's the case of a dynamic contact angle. So with this, I will conclude this lecture, and I'll see you around in the next lecture. Thank you.